Well, I think we can start, and then people must drop in as they are finished with their coffee. Good morning. Welcome to this session about energy management of buildings through real-time self-assessment and optimization. I think the background we have here is that we have a building sector where we are not too happy about the performance. Many buildings are not performed as we expect or as we want them to do. So we need to, you could say, do something to improve these conditions. On the other hand, we are also in a time where more and more data about building function and building performance is becoming available. Today, most manufacturers have installed IoT devices in their products or systems. They are connected to the internet. Manufacturers have access to them and can see how their products are working and functioning and can make changes if something is wrong. But these are a number of, I would call them data islands, because every manufacturer cares about their own data. And nobody is looking across and looking at it in a more systematic way, exploiting, you could say, the data from different manufacturers, from different systems, and taking care of the overall performance of the system and the buildings. And this is necessary if we are going to improve the performance. It's not enough to know that a pump is running and is performing as the product should do. We also need to know, is it actually the right pump for the task? Or would it be better to replace the pump? Or would it be better to control it differently to get a better performance? And the only way we can do that is actually to look at the whole system. So what we are looking at in this SATO project is actually how can we, you could say, continuously, systematically, automatically assess the performance of buildings, provide guidance on improved control, or maybe guidance on decision support to make changes to the system to improve the performance and optimize it. Yesterday we had a workshop where we presented, you could say, the concept of the project, our, you could say, communication and calculation platform, and so on. Today we will give some examples on how this methodology can be applied in specific buildings and how using these methodologies actually can provide some new insights that can help building managers improve the performance of their buildings. And we have selected, sorry? Not on camera, okay. We're better now? Yes. Good. So remember, when you come and speak, you need to be here. So we will give 4 different examples on how different methodologies can be applied and what the benefits and outcome of these technologies are. They are quite different, showing, you could say, the breadth of our work. And I think now I will invite the first speaker, which is Simon, to talk about how real-time energy management and fault detection can improve the performance of an office building.
So I'll do this one, so I'm sure I'm in camera. Thank you, Per. So my name is Simon Melgaard. Just to quickly present, I'm a research assistant at the Aalborg University, and I've basically been working everything within building optimization and data analysis in buildings. What I'm going to talk to you about today is mainly fault detection and how to better assess if our building is performing as we expect. But just to give a slight background before we dive into it, generally when we work with buildings, we have the concept of commissioning. Inside commissioning, we have the classic one. We have what is called here initial commissioning. So we commission our building before it's in use, and then we forget about it. Then sometimes people start doing either retro commissioning or recommissioning, depending on whether or not there was an initial commissioning, which is fine. You get a one-time update of the building performance, you see if it works, and then you basically leave it to be itself again. But what we're going to talk about today is the act of continuous commissioning. So it is basically using continuous building data to actually constantly monitor the building in order to not just have single-time assessments, but constantly get an overview of it. If we go into what then is continuous commissioning, it includes a lot of different areas. What we're going to focus on is the maintenance part of this. So here you'll generally hear words such as reactive maintenance, preventive maintenance, and predictive maintenance. So these are basically at what phase we are focusing on, if we're trying to predict how it's going to perform, or if we're trying to just simply figure out, is it performing right now? And that's where we come in. So we're going to focus on the reactive maintenance. And there we're going to talk about two things, both manual fault detection and automated fault detection. But first of all, we need to talk about why can we actually now start doing fault detection. And as Pierre mentioned, we're slowly getting more and more data from the buildings. We're getting more and better building management systems. They are slowly starting to actually be able to get historical data, depending on the building and system. Sometimes it's historical means the last week, sometimes it means the last several years, which is a bit of an issue. But to start out with fault detection, we already have the classic simple versions available. So that's the threshold-based alarms. So you said, if my system uses more than, I don't know, as an example, 10 kilowatt of peak power, then we have an issue. It shouldn't do that. That's classic, but it makes it very difficult to actually assess the building in practice, and it is very inflexible to, is this actually what the building is supposed to? So generally this will help the maintenance personnel by identifying faults that can be not that easy to necessarily find, such as abrupt drops in performance. You may see them, but it might be half a year later when they actually start influencing the performance of the system. It might be faults that only occur under very specific conditions, so it might be only in very extreme cases, so very cold weather, very warm weather, or something else. Or it might be faulty components that aren't necessarily directly visible in it, but will affect the performance. So in order to do fault detection, as I said, you need available data. So what we found out in this project is, even though we had our building is from one of our case buildings, we're also going to use this, is from 2016. So it's quite a modern building, but still we had no way of basically collecting or storing historical data that was older than generally 1 month, and it was only for a few data points. The reason for this is that in the building management system, everything was stored locally in it, and it had realistically no way to expand the storage. So what we did is we built a separate database that actually collects the entire historical data, permanently keeping it, which both allows us to attach an API so we can actually use the data as third parties, but it also improved the performance of the building management system itself. So it's actually also acting as an extended database for it, so the building personnel can also use it directly there. So if we shift to the manual fault detection, which is also, let's say, the classic version, you have some data, you have people that actually just look at the data. This is the one we have here. Then we have suggested several improvements in different steps on how to actually go from having time series data to actually having what we call contextual data. So if we look at the classic version, here you see a time series graph. So this one could be a version of how you could assess if the heat efficiency of a rotary heat exchanger is actually well. So normally we know it above 80%, it's not that bad. But that arises the conclusion or the issue. Should it be 80% all the time, or are there times where we shouldn't actually have high enough efficiency? But as you see here in the green one, in the green curve, it's not that easy to assess if it's actually performing well under the conditions it's performing under. So from this we tried to go to making visualizations that actually provide a lot more data. So what you see here is the completely same data. Now we just see the heat recovery as sort of a function of the outdoor temperature and the this rotation speed of the heat exchanger. So what we actually now see is that yes, as the outdoor temperature increases, our heat recovery will fall, but it's not necessarily because of the outdoor temperature, it's actually because the rotation speed decreases to match system performance. This is very nicely, but it won't give the operational personnel a single value that they can actually quickly use to operate. So what we then progressed from this was to try and combine all this data into a single KPI. So it's the one you see here in the blue. It's the one we have called, or shortened as URED, which basically is Useful Heat Recovery Efficiency Deviation. What it simply means is that we assess how much heat recovery efficiency do we actually have compared to what could we actually use. So if you look at the in the green marked areas, we have the first area to the left in both for both the air handling units. In this case, we're in the winter situation. We have heat recovery efficiency that's lower than what we could maximally use. So the heat recovery efficiency is the black one, and the maximum useful heat recovery efficiency is the red one. In this case, we could consider if we needed a better heat recovery, better rotary heat exchanger. It might not be worth it, but it's not an issue. We have a heating coil to compensate for exactly these situations. If we then move to the second area, so in the left plot it's in the bottom, and in the right plot it's in the middle. Here we see optimal performance. Our heat recovery efficiency is exactly where we would like it to be. So if you look down at the blue URED, it's close to 0, which is basically what we want. But then we come to the issue that's not normally identified at all in the heat recovery efficiency. It is the cases where we're actually recovering too high amounts of heat. So we actually have an efficiency that's higher than what we would like. So it's what we see in case 3, where it becomes clear that we are recovering more heat than we need, which can lead to basically one of two cases. Either we will be supplying a higher temperature out from the air handling unit than we would like, or we will need to apply cooling to it in order to reach our target, and that's of course not desirable. So in this case, there's definitely room for actually optimizing the performance or the control strategy of the heat exchanger. So this one was for the operational personnel directly. If we then focus over into automated fault detection, we take first a little bit look. So what should an automated fault detection algorithm actually provide? So in this case, as it's only fault detection, it should generally provide an alarm. It will give information of when something is faulty in the system, and it can range anywhere from static thresholds, as mentioned earlier, the classic version, all the way to advanced machine learning models. But in order for these algorithms to succeed, there are basically opposing goals. So of course we would like to find all faults. That would be nice. The issue with trying to make an algorithm that does this is that we have a very high risk of adding too many false alarms, which has been found to decrease the trust in the system. So the moment the system, even if it finds all faults, if it also adds a significant amount of false alarms, the operational personnel has a risk of simply not trusting the system and thereby ignoring the fault alarms. So once you do this, you need to actually make a trade-off between performance. So where should we lie? Can we accept that we find 90% of the faults if it means that we then don't get the false alarms? This will be highly individual and depend on building and system, depending on how critical it is for the operation. But another issue to also notice is the trade-off between performance and interpretability. So once we go to the more advanced models, you can either have what is known as white box, black box, and gray box models in order to predict it, depending on how closely they are related to physics. So if you go for the neural network and all those type of models, you get black box, you get an answer. They're normally quite good models, but you have no way of knowing why you get that answer. So what we have done in this case is go towards, it is still using clustering and machine learning algorithms, but we still retain some interpretability by actually saying we investigate under specific conditions. So we try to block them into conditions, which is what you see here on the figure. So if you look at the lower bottom right figure, this is the red square is basically our current operational point where we will then investigate if there's something faulty under the same conditions. This is a lot of information. If you'd like to read more about it, we have a preprint available, but we are also publishing it in the meantime. So what do you actually normally get out from a fault detection algorithm? In theory, you get a 0, a 1, you get a fault or no fault. So this is basically what it would look like if you have no interpretability. You just get a graph of fault or no fault. So in order to do this in SATO, we try to also visualize the conditions it's operating under, adding a lot more information. So how does it normally operate under the different conditions, and where is it that it's actually faulty? Yeah. So to summarize what we have found is are the main key points when doing fault detection is, first of all, we need to ensure that data is accessible and of high quality. Without ensuring this, there is no point in actually going further. This is the starting point for all fault detection. Then we need to provide the maintenance personnel with good information to ensure good decision making. Once we have these ensured, you can start focusing on ensuring contextual information so that it becomes easier to interpret KPIs. And only when you have these available, then it would make sense to start doing the automated fault detection. But it's still important to ensure that you provide simultaneous information for the operational personnel. That was what I had for this one. So just to provide what the next step is. Now we focused very much on the operation of buildings. So our next step will be to optimize the waste heat potential of buildings and actually take it further, so integrating data centers. And if you'd like to know more, this is the next project we're doing. From that, I would just like to thank you for your time and give the word back to Pia. Thank you.
Thank you, Simon. The next presentation is a little bit different because there we would like to show how we can use the BIM as a tool. Oh, the camera again. Sorry. Thank you. Yes, so in the next presentation we will show you how we can use BIM as a tool to, you could say, visualize the performance of buildings and get, you could say, building management and users better opportunities to actually, you could say, get information about the performance. So please, Pablo.
Hello, everyone. I think I'm in the right position.
Yes.
Yeah, and this is to. Okay. So, I would like to talk about BIM integration. And when we wrote this project, we thought it was quite interesting to integrate something that the industry has already implemented in their offices. In order to have new ways of visualizing this data coming from buildings. To begin, I would like to start explaining you a little bit my point of view about BIM. You know, I think all of you know what's building information modeling. I think the easiest way to understand it is having a 3D model with geometry and some kind of data. Data about energy analysis, data about acoustics, structures, LCA, whatever. As long as we have these two components, we have a BIM model. And then there are some discussions about if BIM is a technology or it's a methodology. From my point of view, it's both of them. We are going to work with new processes, and we are working with new tools. And this is what we have tried to do in this project, creating new tools adapted to the existing new processes. Surrounding BIM theory, there are a lot of acronyms. It's quite difficult to understand the meaning of all of them, but we consider interesting working with some of them, like IFC. We are been working in an open environment, so IFC is the standard of interoperability in order to promote the connection between different tools. We are working with a common data environment in order to promote the collaboration between different stakeholders. And then we are researching about new ways for representing this data with new technologies like augmented reality. Okay. This is not something new, so getting BIM models in order to calculate energy analysis is not new. We have been working in this area, focus on the design phase. In that way, we developed many years ago the CYPE term tool. And with making some kind of processes, we were able to import an IFC, include extra data like second space boundaries, and then calculate the specific standards of different countries like France, Spain, Portugal, Italy, or Morocco. Here, again, is about the same. Here, we are considering geometry data, but we are including extra data, like weather data, schedules, construction systems, specific codes requirements. And now what we are trying to do is, okay, let's include real data coming from sensors or assessments results. Based on this analysis, we are also working in new areas, new projects, in order to calibrate this analysis, thermal analysis coming from the design phase in order to adapt it to the real situations. But let's focus on this project, and here the idea is, okay, we have BIM model, let's feed this model with real data in order to obtain a digital twin. So let's work and check what can we do with this information. As a result, we got this application, OpenBIM SATO. It's a free tool. And the idea in OpenBIM SATO is, okay, let's get information from a cloud platform like BIM Server Center in order to integrate BIM models in open formats. And also, we have created a connection with the SATO platform in order to obtain data from real buildings. We have defined some ontologies in order to create the connection, and this is something I would like to explain to you. Okay. So, first of all, we need to put some order, specify which IDs are we going to use. And in this case, we were working with IFC models, so we decided to, okay, work with IDs in order to obtain the title of the project we are considering, but also the IFC ID, the ID of the different IFC spaces and IFC zones. So with this consideration, we were able to create a link between the BIM models and the database coming from the real buildings. And then we have included some extra analysis in order to control that you are placing the sensors in the right place. So this is one of the features of the application, is helping designers to create this infrastructure or to design this IoT infrastructure in order to optimize the distribution. So in that way, we are controlling the IFC air terminal and IFC unitary equipment, the HVAC system, in order to avoid, for instance, placing sensors close to the HVAC installations. No? This is one of the rules we have implemented. Another one is we can control the IFC walls, and we apply a volume in order to avoid placing temperature sensors close to the facades. So once we have done that, we need to represent the data coming from sensors. We have temperature, CO2, humidity, and it was quite important to represent it in a graphical way. So you can directly see a 3D model and check if all the different spaces were in a good condition. And then if you wanted to visualize the historic, having the opportunity to check how has been the evolution in that room. Okay. Something similar with the assessments. This assessment gives us information about the real performance of the building. We have a lot of assessments in our project, and we have been implementing some of them. Right now we can visualize the air quality, the occupancy, but also the thermal comfort of the different spaces of one BIM model. No? In any way, I think the best way to understand how it works is with a short video. So I will show you quite in a quick way how it works. Okay. So this is the OpenBIM SATO tool. We can import BIM models in IFC, and then we have this possibility to locate sensors, where here we have applied some specific rules in order to control the height range. So we can control the sensor are in a good position or the distance from the HVAC system and so on. Then when we import the data from the real building, we can visualize all this information graphically in 3D view with some specific colors that we can modify if we want to control, let's say, if there is one room above this data or below this data. So we can get the red alarms and so on. No? Something important is, okay, here we have this part of assessments in order to control the performance. Here we are checking the air quality in real time, so we get the last value, not only for air quality, but also for occupancy level, thermal comfort, and so on. And then we have been researching about the possibilities of visualizing this information in augmented reality. So by this way, we can integrate some new stakeholders like occupants in order to represent this information. Here we have some ideas about the evolution of this tool, how to apply it during the construction works in order to optimize some specific processes. So I think the connection between having data and representing it in some specific formats is quite powerful, and we will be researching about that in the future. So to sum up, this is the workflow. We can identify, if we think as OpenBIM SATO as a product, we can identify two main uses, two main scenarios, focus on different stakeholders. On the one hand, we have this design phase, where we offer to architects, engineers, whatever, the possibility to have one tool to integrate all the different sensors and actuators in a BIM model and control the definition of this infrastructure has been defined well, according to some specific rules. And then we have the other use of the tool, which is getting the data coming from the real buildings and making some kind of energy analysis in order to improve the behavior of the building. No? So here we are in an operational phase. No? In general, this is the workflow. We talked at the beginning that it's important considering workflows when we talk about a BIM. And in this case, we import a BIM model, we define the rule analysis, we obtain the volumes representation, then we import the data coming from the building. We can analyze this sensors data and assessment data. And then, to finalize, we can obtain some reports and some representations in other formats, like augmented reality or virtual reality. Okay? And I think that's all. So maybe you have some questions or whatever. Thank you very much.
Yeah, I think we take thank you very much, Pablo. I think we take the questions in the end and have the discussion. But anyway, our next presentation is by Nuno, which will also show something about continuous self-assessment and observation, but now in a student workplace. So please, Nuno.
Thank you. I'm Nuno. I'm a postdoc researcher at the Faculty of Science in Lisbon. And I'm going to show you some of the developments in the SATO project at the library building and in our faculty in Lisbon. So a bit of a background on the definitions. So self-assessment is pretty much the building being able to assess how its own status is at any given moment. And then we can use real sensors that measure some physical variable like temperature, or you can use soft sensors that use these other real sensors, and probably even other soft sensors to measure something indirectly through some algorithm that you can't measure directly. Then use that information for self-optimization, where you can correct how the building is operating to improve energy consumption or thermal comfort or improve flexibility opportunities. You can use that. So the library is here. It's in Lisbon, in Portugal. It's this building. You can't see too well, but it's not too bad. It's not the prettiest of buildings. And in the context of the project, we have equipped the building with many sensors. This is one of them. It measures temperature, CO2 concentration, and humidity of the air. We're also measuring temperature of the thermal mass, but those don't really have any pretty pictures. And we're deploying these sensors in multiple spaces. I don't know if this has a pointy thing. No, it doesn't work. So we have this main central atrium where we have these sensors. We also have two separate rooms with their own sensor. And we're measuring as well in height, so we can see if there's any kind of stratification of CO2 or temperature. And so this is this is only for assessment, so we can see how the building is behaving now, and based on that we can then act. And to act, we have these motors on windows. These are on the main floor, so they pretty much just tilt the window open or closed. And they're on the main floor, both the north and south sides, and we have a bunch of them. We also have these other windows on the top floor, where you have like two pieces of glass that turn and open up that way. These we only have on the south side. So this is for temperature, and then for temperature control of thermal comfort. We're also acting on lighting. So we have these illuminance sensors, and we have these dimmable luminaries that kind of look like trees. And these are also on the main floor of the atrium. They're only on this central part, which has the most sunlight and where we can act with bigger effect. So all of these are for assessments and optimization, which we call services. And the first main assessment is whole building energy. So how much does the building use, all of the building uses in energy. So for our library, we're using about 270-ish kilowatt hours of electricity per square meter. And that number alone doesn't give much information. So my colleague Frederico looked at a database of a few hundred or a few thousand buildings to see what different kinds of buildings use, how much energy different kinds of buildings use. We did a lot of statistical analysis. So this is the distribution, and we're an educational building, so we're a bit on the higher side. So there's some room for improvement. And so this is the main basis. As for other assessments and services, you can go to lighting. Some of them are, which is quite a straight to the point assessment and service. And so this scheme makes it look way more complicated than it actually is. We basically use those illuminance sensors. We measure the average illuminance, which for an office or educational type building, we want it to be about 500 lux. So we fulfill that average illuminance check KPI, but we don't want one place to have 1,000 lux and another one to have 0, which would fulfill the average, but would not be a very good system. So we also look at uniformity, and that is pretty much just the ratio between the worst point and the average. And you will want that to be above 60%. So that is the assessment. It's just how good is the lighting at any given moment. Then we have the service, which acts on that assessment. We can either have good lighting, and that's pretty much it, so we move on until we need to check again, or you need to fix it, because you can have too little lighting, and we can use the dimmable lights to turn them on a bit until we have enough lighting, or if there can be a lot of lighting, because there can be sunlight, and we don't need the artificial lighting, so we can turn off the artificial lighting. We can also have good average lighting, but bad uniformity. In that case, we turn on the places that are low, that have lower lighting until it's okay. And then you just repeat this cycle to ensure that you have good lighting in your space. So other assessments and services are not as straightforward. And this one is the natural ventilation aggregated control, where we want to reduce HVAC use. So we saw our building uses a lot of energy. A lot of it is for HVAC, because it's a building that has a lot of occupation. People heat up the space. The computers that the students use also heat up the space. So we end up needing to cool a lot. And Lisbon is also a warm place, so that also helps. So we want to reduce HVAC's energy use, mainly for cooling and for ventilation. But there's always the question of when do you turn that off and open windows? For how long do you do it? And how much do you end up saving in energy? So in the context of the project, we have one assessment where we have a soft sensor to calculate the airflow of natural ventilation. So you don't have like a real physical sensor to measure that. You need some sort of algorithm to calculate it. And then we have a service where we predict what would be the impact on savings based on current indoor and outdoor conditions, and based on the assessment of the soft sensor to predict how much flow we would have. And then we decide if we open windows or not, if we close them. So the assessment pretty much works with this 4-stage flow. We start first with, we need data. We need data from the indoor environment. We need data from the outdoor weather. And then we have an RC model, so one of those models where you kind of compare heat flow with electricity flow. So if the heat flows through a surface, you have a resistor. If heat builds up in a surface, you have a capacitor. It's a 2R2C model, so it has 2 of each. And we use that to calibrate how the building works thermally. And then we need to test how does the building behave. So we have different number of windows that are opened, different areas, different differences in temperature between outside and inside. And then we have several measurements, and we see how that behaves. And then we train our model, and we end up with a model that predicts NV flow. So I'm going to show you some of the pictures of our experiments. So this is the inside of the library. These cylinders are there to mimic the heat flow of people. So we did this when the building was unoccupied, so we can fully control the behavior of indoor loads. So we have these people to represent the cylinders that represent the heat of people, about 2/3 or 3/4 of maximum occupation. And we use this to calibrate the RC model of the building. Then to calculate airflow, we filled up the room with CO2, a predetermined amount, to have some amount that would be measurable, but not too much that it would be dangerous, otherwise no one would do the math afterwards. So we have these fans to distribute the CO2 in the building. We have this one, that other small one, it's the same size as this, just far away. And so to ensure that it's uniformly distributed, and then we just wait for it to settle and be uniform. So we also use those other sensors in height to ensure that the uniformity is in all dimensions. And then after that, we can open the windows and see the airflow. So we have these smoke machines that's sideways for some reason. So this is on the top, so you can see that the smoke is going outwards, so we're on the outside. Those are the windows that tilt. And these are the windows on the inside, where you can see that the flow goes inside. So we were making sure that the flow behaved the way it's supposed to, and it did, which is always good. And so these are some of the results. So we have the prediction of how the flow is, and this is a prediction, this is a real flow, and then we would use our model to see if we got the values that we measured. And we have some good matching. Obviously it's not perfect, but it is quite a good matching. So based on this assessment, we can then develop the service for partial control. So again, we need data, same data as before, indoors, weather. We need the same RC model. And then we did more training, so we used the points from before, where we had no people, just a cylinder. But we also had measurements with proper people, with the building in regular use, with the students and all the people that work there. And we trained a neural network to further develop the soft sensor. And then based on that, we can have an MPC, so a model predictive control, to see how that would behave if we open the windows. So at any given moment, we assess how much flow we would have and what impact that would have on savings. Then based on several constraints, so if you open the windows, you turn off the HVAC, but you would only open if outside was cooler. So there are many constraints to get the result that you would want. So you train this model. We do have some results. So these are two separate days. There's a day of lower enthalpy, so a cooler day, where you have overall lower needs for cooling, but you can get
3 days each.
there are 3 days each. Okay.
Dark blue.
Yeah.
Similar 3 days.
Yeah. They're similar 3 days, each that have the same enthalpy. So the baseline for cooling is lower when the outside is cooler, but you can also get a lot more cooling effect from natural ventilation, which is even boosted if you cool at night when no one is there. On warmer days, you end up needing a lot more heating, and it's also more difficult to cool down when the outside is warm. But there is a good principle. The results are quite promising. Of course, the model still needs fine-tuning, it still needs development, but it does seem to be a good step forward in being able to control buildings, see how they behave, see how you want them to improve their own both energy consumption and thermal comfort. And yeah, that's pretty much it. And then the questions are for later.
Yes. Thank you, Nuno. It's a pleasure being a moderator of this session, because all the speakers are doing very well and keep in time. So we will have plenty of time for questions and discussions afterwards. So I think that's perfect. So the next presentation will be by Frederico, focusing more on indoor environment and in another type of building, which will be in a store instead. So please, Frederico.
Yeah.
It
is open?
You should not.
Okay.
You naughty boy. What will you do?
Okay. Maybe it's on. Yeah. So I'm Frederico. I'm a PhD student at the Faculty of Science of Lisbon, and as Per said, I'm here to talk a bit about the retail stores. There are two retail buildings in SATO. It's the pilot that we have. Beginning with a bit of contextualization, we all know that buildings do use too much energy, but what about retail? We can see we can see during the review that we have done in SATO that retail stores do use more energy, than the other building categories. In here you can see the retail that are the pilots on SATO. They are located near Lisbon, one in Amadora and the other in Seixal. On the right side you can see a representation of the buildings that are the image basically. They have similar-ish useful area. They both have two rooftop units as the HVAC system with also similar heat capacity or cooling and heating powers. In here you can see an image of the stores, on the left from Seixal and on the right Amadora. During the project, to explore different assessment and services that have been discussed before, we installed 5 motorized windows to explore the potential of natural ventilation. We installed in Seixal 3 power meters, 1 for the whole building electricity use and 2 for the rooftop units. And in Amadora, we just have installed 1 power meter for the whole building energy use. Mainly the idea is to compare these both stores, a deployment of assessment and services in the Seixal store and compare it with the Amadora store. We also have installed temperature, relative humidity and CO2 sensors, both in heights and also in the thermal mass of the building. To collect information about the occupancy of the store, we have connected the already deployed occupation sensors in the store. We have installed interior shades on the Windows 20 in Seixal store and the luminance sensors. Here the idea is to explore the visual comfort, as is the service that Nuno described before. And also here we are able to explore the use of daylights and control the solar heat gains using the interior shades. In here you can see the list of assessments and the services that are deployed in this store. There are a few, so my idea is to show you an example of one of these services, mainly the self-calibration of digital twin that has to deploy also 3 or 4 assessments to be run. This is the name, basically. To deploy this service, we have to deploy all these assessments, starting with the whole building energy, going through occupancy level, and building as a battery, thermal envelope, rooftop unit, and sizing of EBCs. By doing so, this is another depiction, just a representation. Regarding the whole building energy, we collect information about the use of energy at different frequencies. Here we can see that in Vorten Seixal, I forget to say, I'm showing the example of Vorten Seixal. We can see that we are using less energy than the median, and the pattern of the use is more accentuated than the ones that we expected. Here you can see a visual representation of the actual deployment of the building as a battery and thermal envelope assessments. We start by heating the thermal zone using the HVAC. Afterwards, we can shut it down and let the thermal zone to cool down and use this decay to fit the U value of the building envelope and the light and heavy thermal effective thermal capacity of the building mass and the furniture. Regarding the rooftop unit, here yeah, the idea is to, this one is a depiction of the assessment do it in a heat pump, but basically is the same, but just using the air, the part of the system. Basically, what we have done is to assess the heat transfer in the heat pump, and with the electricity use, we can get the COP, and afterwards we can get the efficiency by doing the ratio with the COP of Carnot. Here are just some equations that we have used to calculate the enthalpy variation and the COP in different modes. To assess how much airflow, outdoor airflow, the rooftop unit is putting in the space, we have done an experiment changing the outdoor opening position and using CO2 gas as a tracer concentration to assess how much airflow we are putting outdoor airflow with the use of the rooftop units. Now I'm presenting just the scenarios that we have deployed. The scenario 0 is just the data. Scenario A is the simulation in a building environment, the Energy Plus, a simulation with design parameters. The scenario B is the A plus assessed room parameters using the RC model, and scenario C is the B plus the assessed HVAC parameters, in this case, on the rooftop unit. These are just an image of the building. Okay. Here we can see that using a validated model with design parameters, we get a good agreement. But when we add to the thermal simulation the assessed room parameters, you get a better fit to the measured temperature on the thermal zone. Okay. Heading the assessed parameters of the HVAC, we get even better agreement between the model temperature and the measured temperature, and also the same in the electrical demand of the HVAC. I'm also showing you guys an example of the same deployment, just a result at the faculty of the library at the Faculty of Sciences of Lisbon. It's also a pilot of SATO. Okay. Basically the same. Starting with the simulation using design parameters, the agreement between the model temperature and the predicted, the measured temperature is not so good. By adding the assessed room parameters, we can go to a better agreement. Yeah. And finally, introducing the assessed HVAC parameters, the agreement is even better. We also have a better agreement in electrical use, as you can see, comparing the green one with the red one and the blue one. The next steps is to test and implement the outdoor floor assessment method using the CO2 tracer as a gas, and consolidate these results and trying to finish the paper also. And basically, it's it.
Thank you, Frederico. So now it is finally time for questions. So I think we start with questions, then we can continue with the discussion. So anybody having any questions? Yes, please. Yeah, maybe you should do this because those online can also follow it.
What is the accuracy of the temperature sensors? Because the difference were like 1 degree. 1 degree may be inside the variation. 0.2%. 0.2 degrees.
Yes, Then we have the discussion if the sensor is located at a representative place, which is another question. Yes. And any other questions? I have a question for Nuno, because of course it's quite impressive that we can do these calibrations and get quite accurate results. Have you had the opportunity actually to test the methodology in the building and see if we can, you could say, achieve similar results when we apply it?
So I think maybe João can explain the measure.
Yes, yes, we tested in during 2 weeks using different approaches. One week was just natural ventilation during daytime, and the second week was daytime with night cooling, and the results were, of course, it's not a perfect prediction of the natural ventilation flow. However, I think it's a very good accuracy with I think an R square of 78%. So I think that's not perfect, but it's.
Yes, of course. Now, of course, the Nuno showed quite impressive savings. So that was also
Yes.
my question.
In a mild day, I think that there is the possibility to avoid completely the HVAC, and in the warmer day we still need the HVAC, but the savings is like 30%, as we find in the more or less in the literature.
Okay. So it was actually quite successful for this short term, demonstration. Yes. You have a question, Gillian? Yes.
Question for myself.
Well, then you know the answer.
Is that possible? So I'll go with the question and the answer. No, I just was trying to help, because I think what Nuno presented and João worked on and all of us is quite complex, in the sense that, just to clarify a little bit, what's the main challenge of having a natural ventilation system in a commercial building such as this one, and then controlling it successfully? What's the challenge? So the main challenge is to begin by saying that whenever natural ventilation is used, the conditions should remain within the acceptable range of HVAC. So no special Olympics for natural ventilation, in the sense we still need to be comfortable. So we always had the same temperature range, whether we are with open windows or HVAC. So the idea is for users not to notice a difference. So that's a starting point. Then what's the challenge? The challenge is, under a given condition of wind, internal temperature gains, and outdoor temperature, so it's a huge set, given the conditions, can I open the windows? So I have to predict the airflow that results from all these conditions, and that's where all the neural network and soft sensor that they were presenting, what it tries to do is predict the airflow. If I know the airflow that I'll obtain, I also know the cooling power, because I know the temperature difference between indoor and outdoor. If I know the cooling power, I can use the natural ventilation as an air conditioning system, let's say, as a natural air conditioning system, whose power I'm aware of, and then I can control. I know this was very long, but that's the concept. I think you all know and understood, but still.
Yes, thank you, Guillaume. We probably need some time to digest. But I think the vision by the project was actually, and this is in the word of self-assessment, self-optimization, that these are some things that could be done automatically. So you did not need a great effort actually to make it work. I'm a little bit worried about this approach, because when I look at this, it seems it's not that easy to get to work automatically, because there is a lot of assumptions. There are some, you could say, different you could say, analysis and measurements and so on that needs to be done to get an accurate solution. So this means that it requires quite a lot of effort maybe to make it work. And then I'm worried about application. Will it get a large-scale application if you need, first of all, to have the expertise to do it. You need to spend time to do the work to make it work. So I was actually wondering if it was possible to get a benefit without doing extra experiments, but just base it on what are measured in the building. Of course, the accuracy is not the same, but maybe it is a good step on the way, and with much less effort. Would that be a possibility? Yes, you have a comment down there?
Perhaps here we are facing a problem, is that people in other countries in Europe, they don't have temperatures difference as we have in the south, okay? So we may have like 15 degrees of difference. So it is, I mean, common sense for the population to open the windows at night, okay? So the intention of the project, I understand very well, is to do it in a very scientific or technical way, but this is a common practice in these countries. Okay, so when we see that some strategies for HVAC control, they always consider the windows must be closed. Okay, I think people in the south is terrified because they like to open the windows, especially in the springtime or in autumn, and to have fresh air from the outside, because it's not an aggressive weather. The weather is helping you. Okay, so I understand the purpose.
Still need just to clarify. So Per, I think all our effort, the whole algorithm that Nuno presented is thought out as self-deployable. That means it uses the HVAC system to measure continuously internal load. That's quite exact. Can you move them now? And so it measures the thermal load of the space with the HVAC. And then anytime you open the window, either the system did it to learn or someone decided, it has a measurement event for calibration. So the rationale of this system is zero human intervention and a learning period. I think we have a consistent solution for that. That's what we think. Of course, in the development that we showed here very briefly, a lot of effort was spent in understanding if it measures well. Putting all these loads in the library was crazy. We were doing 20 kilowatts of electrical load inside and so on. But in fact, this is self-deployable. We claim.
And we tested different natural ventilation configurations.
Yes.
Different open areas.
Yeah.
And there's many of us.
But I like to challenge this because a simple rule-based methodology, how effective could that be? Just saying if there is a cooling need, you have the coolers running, you have a certain temperature difference between the space and outside, then you can open the window and you will reduce the cooling need of the cooler. How far will you get by a simple approach, and how much do you add by doing this more complicated?
You get as far as we got, with the exception that as wind comes into play, you have an extra complexity here.
Yeah.
But what our system does, you could think of it as a self-learning of a simple rule-based approach that's suitable for
Yeah.
that building. That's all we're doing. But we don't need to write it in a piece of paper. And for each building you have different rules, because the delta T is different and so on. But that's a good point. That's
Yeah,
I'll say it again, so it's not even better. What we did, act surprised. So no, what we're doing in fact is a system that learns the rules for the building. Once it learns, the rules change slightly with wind and loads, but we're doing rules. But the main strength of what we did, in my opinion, is an automated rule gas system that is tuned for the building, and that is really nice. In the end, things are quite simple, and the decisions it makes are simple. but they are suited for that building, those loads, so it's really nice, in my opinion.
Yes, so your point is that all what you have shown here is just to get a better starting point.
And a continuously updated.
Yeah, and then when you have a good starting point, then actually you are continuously self-learning the system. Yes.
Just like that.
Then the question is, could you reach the same result without this preparation of the model? Just run a self-learning algorithm instead. Could you reach the same result? It might take a longer time, but if it's a month or two, maybe it's not that important, just considering the lifetime of the building.
Then Pedro should answer, which is a great question.
Well, of course, in the project, we did not reach the stage of making those tests. Only in very basic simulations, which to me don't have yet a stronger meaning or result that we can make strong conclusions from that. But short answer, I think what you said is possible, to have a system that self-learns, but we need, and that does more or less the same that Guilherme was saying. That might be easier to scale because it will have less software parts that you need to adjust and to make. But it will require even more preparatory work. So in my view, that self-learning system that can be done needs first to be developed over a simulation model. It can be the simple RC models, it can be physics in Energy Plus or other tool. And we can try to teach that learning algorithm using these models before it is deployed in the building. Many learning algorithms, if you just unleash them on a real environment, in the beginning it will be disastrous. So you should not do that. You need to do first part of the work offline with some simulation model just to make it behave well in extreme conditions and boundary conditions and so on. And then it can still learn with time in the environment already without making serious problems. That would be the approach.
Yeah. Okay, thank you. Guilherme?
Yeah, just quickly, just to say, I think that this is a great discussion. I don't know as much, of course, as Pedro about learning and all this. I'm just looking at ChatGPT and all our experiences with self-learning, reinforcement learning, whatever the name. I think what we're doing is smart, because we're breaking the problem up and we're not asking for the learning or the AI to do everything at the same time in a way we can't control very well. So that's why I think this is an intermediate approach where physics is involved, but there is also a neural network.
Thank you. I think we have closed this discussion. Then my question is, anybody else having another question or another discussion item they want to raise? I think it's a great vision, a great vision to have this approach. We want to do that buildings can automatically assess themselves and come up with ideas on how to improve. But I think there are also a lot of barriers actually to realize such a system. Of course, when you look at a car, then it tells you how long time is running back. It tells you continuously how much energy you are using, how much do you gain by breaking down, and there are a lot of information that continuously assist you in getting knowledge about how does the building perform and what is the consequences on you could say on the trip you are making and so on. And if you look at the building side, we are far behind in you could say utilizing the data and the information we have to provide more intelligent knowledge and guidance to people who are in the buildings. And I think we want to catch up and be an industry which are you could say more intelligently using the knowledge and the information we have to provide services and guidance to people to improve the performance. But where do you see, you could say, where are the major barriers we need to overcome from where we are and to such you could say a target? Is it technology? Is it humans?
Human interaction.
Yes, maybe you can elaborate a little bit on this. You have the mic.
Yeah, one of the problems we face is that a main input is the humans, okay? How to model the human interaction with the building. In terms of temperature, not thermal comfort, I'm speaking about how the human feels comfortable, which means that we have like 2 different groups or 6, but women, they don't feel the temperature in the same way than men, okay? And the other point, and probably more important, is ventilation, and how the human is breathing inside the building and how that is interacting with the building. Okay, so in one control situation, as you were describing, okay, everything can be working, but in real life, we have humans. We have humans even opening windows sometimes or doing silly things or running in the building. And for example, in ventilation, the difference you may have if you are sleeping or you are singing or you are, I don't know, doing some sport is huge. So human interaction, as soon as we were able to represent or to manage that, would be the key for a real management of energy in buildings, in my opinion.
Yes. Other opinions on this? I also have an opinion about this, and this is more related to the organization of our sector, because when we look at buildings, you could say we have a lot of different actors who are responsible for their piece of the puzzle. Some is delivering the ventilation system, some is delivering the windows, the shading, and each of those take responsibilities of their own technology. But we don't have a profession taking responsibility for the overall system. How does it function? How does it work? How does it perform? This is left to the building owner. And of course, if you are a professional building owner and it's a larger building, then maybe you have people actually to take care of the management. But a lot of our buildings do not have anybody to take care of the management of the building and take care of that the whole system is working. Actually, most of our building does not have that. And I think as long as we don't care, because I think that's another human perspective, why do we not care? Why do so many buildings not have anybody to look after how it works and how to manage the buildings? It's because we don't care. So how can we change that? So it's natural that we, and again, I take the car analogy, yeah, I can't explain it, because everybody drives their car for service in certain intervals. Get the car tested. Does it pollute more than it expected? Does the system works, and so on? Nobody have their building to regular service every 5 years to see, does it still work as it was intended? What can we do to improve it? Should we replace some of the components? Should we change something in the control because the use of the building has changed, so we maybe need to control it differently and so on. It would be easy to establish such a profession that could do that if there was a market, if somebody saw a need for doing this. And I think it would improve the performance of our building tremendously if we had such a system continuously, or you could say in a certain interval, really checked the performance and did the changes that was needed.
I belongs to the Building Digital Twin Association, and we have begun with the project with a horizon of 10 years. Okay, so it's not for tomorrow, and it's not ready, the technology. And our purpose is not to develop technology; it's to develop the standards. Okay, but the idea is to use artificial intelligence, an agent in real time, because you are right. In buildings, we don't have operators supervising the building. Okay? If there is no operator, no one cares about controls of the building. Okay? You must have a big building to have an operator there. But usually in our house or in many, many places, there is no one looking after the energy of the building. And so if there is no one, it has no sense most of the time to have controls, because controls, sometimes they don't work properly, but no one cares. Okay? But I think that is an opportunity for artificial intelligence to have these agents. This is something not for tomorrow, but perhaps in 10 years we can have that. We have begun doing the standardization of the components, simulation components, with the collaboration of software vendors, okay, to be able to have those components more or less certified and comparable. So you could be doing the simulation in different systems, and theoretical results should be the same. And of course, oriented to real time. So real time is compulsory. With human interaction, with good modeling of ventilation, which is critical, including the weather, of course. And I think it is possible because in other industries, they are doing it. In aerospace or nuclear, in other industries, they are doing it. So we have to transform that technology into construction. But it's a long way, and we have to collaborate with these standards.
Yes, I fully agree with you. This is the way we need to go forward. And again, if you take the car industry, when you drive your car to the mechanics, he doesn't look at the car, he connects the computer and have the computer to tell him what's wrong and what needs to be replaced. And I think we need to go in the similar direction in the building sector. So you don't get a person out and look at the building and check all the systems and so on, but they connect to the data of the building, and then they make the you could say the investigation and evaluation of the performance. Yes.
Just one comment. I think there is one element missing in this discussion and in your analogy of the car, which is the car from an engineering point of view and even software development systems integration point of view, the car is seen as a critical system. That brings an area that in engineering and computer science is known as dependability and fault tolerance, where lots of approaches and techniques are in place to solve typical problems that are well characterized, and that's why the car is so reliable. Even if there is a problem, there is a second approach to make it still work and give you the service that you want. And the building systems integration and construction process, which I don't know very well, but it's not seen as a critical system that needs to be working reliably all the time. Because if it was, you would not have a single sensor to measure one space like this. You have 2 or 3. You would have a voting system, which could be as simple as an average. But an average would not be an actually good approach. Let's not discuss why now. But you would have something that would decide from those sensors what is the actual temperature that I should report. Because if you have a single sensor, this is the most simple example that can be given. If you have a single sensor, You can have all the artificial intelligence that you want. You don't report the value. There are no decisions, and the system must go to a fail-safe approach, simpler approach, or whatever. So there is a lot to be done in terms of how to even install systems and how to integrate them in the building, with fault tolerance as a strong keyword there, and dependability, so that it becomes reliable and working safely and in the correct way most of the time.
Just to say two things. So the revision of the EPBD brings the digital inspections, which are towards what you were saying, and the update of energy performance. So that's one nice, I say, development. And the other, about the analogy, I think it's a great analogy, but cars are reproduced on the hundreds of thousands, similar car, so it's easier for them. Whereas we have, each building is a prototype, so each building is unique, has a unique combination of systems. That explains part of the delay and the difficulties. So each building is an animal that no one knows, no one ever saw before it was built. It brings Siemens, Carrier, different brands together. Whereas in cars, they have a bigger opportunity to perfect. I'm not saying that they're not doing a better job, but it's a different problem. That's why it's so different also.
Yeah, I agree. It is different. Yes, I agree.
What we have in mind in the VDTA is that the big market in construction is renovation. Okay, and thinking on normal apartments, we are speaking about renovation projects of about 20,000 euros. Okay, so changing the insulation or installing one equipment. So the degree of engineering, the cost of engineering we could put there to study the initial state and to calculate the renovation should be in the range of 10-15%. So we are speaking of, I don't know, 2,000 euros maximum to spend on engineering for calculating the renovation. That means we should be investing on the measuring the house, the apartment, buying the sensors, implementing the simulation models, and validation stuff. 2,000 euros. The good point of apartments is that they are not exactly the same, but they always have like 2-3 bedrooms, 1 living room, 1 kitchen, 2 bathrooms. So it's more or less stable, the complexity. So speaking with one engineer of BTT in Finland, he told me that one construction company in Finland told him that if the cost of the implementation of this supervision and evaluation of buildings, if it was less than 2,000 euros, they were going to be implementing that for free for customers, because that was like a marketing tool to create confidence in the renovation status. So this is so I'm supporting you in your project, because all the work we can do for making simulation more confident probably is the key for the renovation wave, to have confidence systems to project renovations, because people today, they don't know what is going to be the profit of the renovation. That is a key point. So if we can provide a confidence system, a reliable system for doing it, probably that's going to be the key for the renovation way.
Thank you. We have a little time left if somebody has another question or discussion point they want to raise. Otherwise, I think I will thank you for participation in this workshop and for the active discussion following the presentations, and close the session. Thank you.